to the moderation portion of this panel. Let's go in the order of presentation today. So we'll start with Dr. Jones, then Culbertson, Dr. Cooperstock, Dr. Istrar, Dr. O'Malley, and then finally Mr. Evan Pezent.
Lynette Jones from the Department of Mechanical Engineering at MIT, and my presentation, I can't remember the title, it was very long and wordy, was to do with tactile and thermal interactions in multisensory cutaneous displays.
All right, hi, I'm Dr. Heather Culbertson from University of Southern California. My talk title was Minimizing Haptic Hardware in Wearable Devices.
Hi, I'm Jeremy Cooperstock from the Department of Electrical and Computer Engineering at McGill University, and my talk was on taking haptics out of the lab and into the wild.
I'm Ali Isra from Facebook Reality Labs Research, and my talk's title was Challenges in Haptic Technologies to Enable XR Interactions.
Hi, my name is Sheila O'Malley. I have a joint appointment in the School of Information and in the School of Music at the University of Michigan, and my talk was on collaborative design of a full-page tactile display.
Hey, I'm Evan Pezent. I'm a graduate student in Dr. O'Malley's lab at Rice University, and I presented syntax.
Wonderful. Thank you all very much for reintroducing yourselves. And now I'll hand it over to Dr. O'Malley to moderate this panel.
Thanks, Zane. So I want to start by thanking all of our speakers for these really fantastic talks. Again, sharing your perspectives on haptics for AR and VR applications, from understanding human perception to user experience design, to even the applications of developing new hardware and software. So I'm going to start with the Q&A question that was left there, and it was directed to Lynette, but I do think it's relevant to a number of us as we think about wearable displays. And the question is, to what extent does the tightness of the attachment to the skin matter for your devices in particular? And then maybe we can expand that out to others as well.
I can start on that. I mean, obviously for any thermal display, it's essential that whatever is heating or cooling the skin is in intimate contact with the skin. And over the years, with all the vibrotactile displays I've worked with, it was also essential to have a tight coupling. You can sometimes get by with having redundancy in signals with multi-actuator displays, so that if the coupling becomes somewhat loose at some points in the display, there may be enough other information coming from the other actuators that the information can still be processed by the individual wearing the display. But certainly they need, it's always the balance, as I think Ali was saying, between not occluding blood supply and causing pain, but also making sure it was firmly attached. And that may just mean you have a very flexible interface that people can set for their own comfort levels.
Anybody else would like to comment on fit or their experiences with fit with these wearable devices?
Yeah, so in our lab at McGill, my graduate students, in particular, Pascal Fortin, have been working quite a bit in characterizing both the perceptual aspects of what happens in terms of the coupling to the skin and how tightness affects the properties of the actuators, as I was describing in my talk, but also on the sensory characteristics as well when you have other equipment that's coupled to it. And they published 2 papers on that subject. One last year that was toward consistent haptic coupling with the Hapti strap, and looking at apparatuses to actually ensure a consistent coupling for the purposes of repeatability in experiments, and a more recent one looking at the sensor signal characteristics.
So I would like to add on top of Jeremy's and Lynette's comments. Yes, if the coupling is loose, then there's perceivability issues that people do not feel it consistently. And if it becomes too tight, then there are sensor issues, but also the comfort issues. But I have also noticed with a lot of these haptic feedback technologies, once the coupling is tight, then it also puts a mark on the skin. So once you take it off, it it's not necessarily annoying, but it does put something on people's skin that stays there for a few hours after wearing the device. So in some of the experiments we did, we found that there is a sweet spot in between where there's a compromise between the skin stiffness uh, as well as perceivability and the comfort. But I'm not sure if that sweet spot varies across different locations as well as different impedance of the skin.
So go ahead, Heather.
I was also going to mention, in our devices, we deal often with arrays of devices and arrays of actuators. And we found with our devices that consistency of tightness across the array is very important, so that you feel all the actuators the same. Because if you know you're putting it on the arm and one side is loose and one side is tighter, then where if we're trying to convey, you know, for example, a touch gesture or motion across the arm, then it does not feel consistent. And so when you're dealing with arrays, it's not so much, you know, whether it's loose or too tight, but whether it's a consistent tightness across the entire array, which is really challenging to design that into the wearable device.
So I want to take this question to Sheila, because she's dealing with very different kinds of devices, right? So with the tactile displays that you described, Sheila, you are relying on a user to come in contact and touch the objects. So I'm wondering how this challenge that we see with wearable devices and ensuring the consistency, how does that translate to your tactile displays, where maybe the way that the user interacts with the device might vary from subject to subject?
That's absolutely right. And one of the issues we deal with in a tactile display is what we call backdrive. So basically, when somebody's pushing down on an actuator, we have to make sure that we're able to take the amount of force that they're pushing on. And some braille readers have a very light touch, and some people, if you see even a printed, like a hard copy braille page after they've touched it, especially beginners, they'll have actually sort of half erased some of the dots. And also there are lateral forces that we have to contend with as people read across the display. Depending on how much they press, they're also going to bring the dots to one side or the other as they move. So that's one issue. And then the second is consistency. Like anything else, braille dots need to be consistent, because if they're not, they're very distracting. So I'd say those two are our main issues. Being able to take the amount of force that somebody wants to put in order for their reading style to be supported, and also then being consistent across the whole surface of the array.
Great, thank you, Sheila. I think I'm trying to decide which of two directions I want to go with questions, but I think I'll go to a question that was actually posted, Heather, during the time that your talk was being played, and it has to do with miniaturization of your Wave device. So maybe you could comment a little bit on your progress in that miniaturization, and then perhaps any others who've dealt with sort of prototyping wearable devices and scaling, and what kinds of issues they've encountered.
So miniaturization is very, very challenging, especially from the actuation standpoint, being able to design miniature actuators. And so really, in order to miniaturize it, because you not only have the size of the actuators, but you also have the controller boards, the wires, any types of connections, to get really, really miniature, we as haptic designers need help from material designers into creating these actual, like, very tiny, like, material based actuators, smart materials that are quite small. But so I'm now in a computer science lab, and so we don't have the expertise to do that materials science work. So we are relying a lot on commercial components that are not necessarily designed for haptics. So valves that are not designed specifically for miniature haptics work, not designed to be wearable, or actuators that are not designed to be wearable. But if we want to get even smaller and smaller, then we do need to bring in the material scientists.
Thanks, Heather. Does anybody else want to comment on the miniaturization of their own devices, challenges with that?
I could comment because we actually have a kind of an interesting problem, which is that, you know, the whole effort to make a microfluidic tactile display was caused by the fact that, you know, there's a limit to how small you can make some devices, like the mechanical apparatus to lift a dot enough so that it will, you know, appear as a sufficiently robust braille dot. They were sort of hitting the limit of how small they could get. And so we decided to come at it from the opposite direction for microfluidics. And our problem is now to make the devices big enough to actually get the amount of travel that we need for the dots as we raise them. So we have that problem on one side, but then we also have the problem of miniaturizing the supporting infrastructure, which includes the fluidics infrastructure, whether it's air or fluid or whatever, plus all the things that need to support that. So it's kind of an interesting take on the problem of miniaturization.
Thanks for that perspective, Sheila. Let me.
Yeah, can I add one last?
Of course.
Moment? Yeah. So in terms of miniaturization, you do run into an issue with haptics, as Sheila said, that there is a certain amount of force required to move. So if you're dealing, for example, with the waves, we are dealing with asymmetric vibrations, and in order to create, you know, the sensation of force or certain amount of vibration, you do have to move a certain amount of mechanical mass. And so there are going, as Sheila mentioned, yeah, there are fundamental limits to how small we can make some of the actuators and still get something that feels strong. So we are going to have an issue, especially in wearable devices, the issue of trade-off between saliency and size.
Heather, maybe in response to the follow-up questions, do you have some ways of quantifying the minimum level of intensity that's needed to create the effect with your wave-based devices?
So it's the asymmetric vibrations is a very, very challenging, from what we found, the asymmetric vibrations is a very challenging problem, a very challenging illusion to quantify because it changes a lot. The illusion changes a lot if I'm moving, if I'm at my joint limits. For example, if I'm over here and I'm pulling to the left, it feels a lot less strong than if I'm over here and I'm pulling to the right. So there is a fundamental mechanical limitation in terms of like how much force you need to actually move the skin to feel that force. Of course, you're going to need less force if you actually put it directly on the skin versus if you put it in a device. When we did test these systems with actually trying to embed it in a rigid system, but then if you embed the actuators in a rigid system, then not only do you have to accelerate the actuator and the skin, but you have to accelerate the mass of whatever you have it embedded in as well. So that's why we decided to attach these directly to the skin so that we can maximize the strength of the sensation. But we have not actually worked on quantifying the, like how much, what's the minimum vibration, but we did find a pretty strong correlation with age. People who are older are less able to feel the sensation than people who are younger.
Jeremy, did you want to respond as well?
Yeah, I want actually sort of a follow-up question to maybe the whole panel here as to whether anybody has experience playing around in this regard with a sort of sporadic, whether it's in the vibrotactile or the kinesthetic domain, a sporadic delivery of a pattern in order to use less power to induce a similar kind of perceptual effect as would be obtained by a single burst of delivery. And that's the sort of issue we've been considering in our needs as well, to sort of maximize the battery life for a particular kind of effect you're trying to generate.
Yeah, so Jeremy, we never played around. We never like studied this directly, but we found that with the asymmetric vibrations, the illusion is strongest at the onset. So if you play a really long asymmetric vibration signal, you're less likely to be able to feel it over time. So it's most strongest at the onset. So you can actually pulse it on and off and then get a much stronger pulling sensation than you can with just a continuous asymmetric vibration. But we have not actually studied this in depth.
Right. So let me go up to the question for Lynette. I know there was a question earlier about the wetness perception, but how does ambient temperature affect skin perception during seasonal changes? Where you might, this idea that 65 to 70 degrees might feel cool in the summer, but cold to very cold in the winter. Maybe it's the opposite of there.
So in our work, we always record skin temperature, and so do most people who work with thermal displays, and that's pretty easy to do. And you do find about well, we're in Boston, so obviously cold winters, hot, humid summers. So about a 4 or 5 degree variation in peripheral skin temperature on average, but so we may have it more closer to about a 33 degrees C, normally more like 30 or so in winter. But so provided you deliver, so everything is delivered relatively. You don't tend to ever work in absolute temperatures because the temperature perception is relative, it's not absolute. The thermoreceptors are definitely not thermometers. And so you then just have your plus or minus 5, 7, 8 degrees based on the skin temperature. And I know there was a question also about humidity. That doesn't seem, I mean, we haven't worked in extreme environments. And I know there was a couple of people who did some work in Thailand where they did find some effects of humidity on thermal thresholds. But you know, most people who do work on this, there haven't been extremes of humid environments to really quantify that reliably.
Thank you. I'm going to take the next question for Ali. With the stereo haptics using multiple actuators, do you have any advice on how to objectively quantify the feeling created from the different actuation patterns?
Oh, yeah. So if you're talking about the number of actuator or the resolution rendered with the device, we use the number of actuators that, although we were exciting 2 actuators, but if people could feel 1 or 3 actuators, or if there's a sense of motion in between them, then we ask that specific question. There's also the quality of continuity, where people could rate it from in some scale, like how continuous is the sensation, or asking for the direction of motion. So in this case, you can some way just justify objectively that if the illusion works or not. I have also seen folks, once they present this continuously, these type of effects, then they ask the user to actually move their body or trace it on the piece of paper. That kind of also gives the indication of whether the illusion is working, or whether people are creating something more dots, or versus it's more on the continuous sense. But in this case, you know, your proprioception may also come in the picture, and I'm not sure how we could isolate that. Yep. But in terms of the frequency of oscillation, I think that one is a total different questions. What we have found that a pure vibration, that is not so pleasant, but once you create these strokes, moving sensation, then they are much more pleasant than individual vibration points. So here you could ask a question about pleasantness, or something on the hedonic scale, like what is the quality of vibration, but that is highly dependent on the frequency and amplitude of vibrations.
All right, thanks, Ali. So I'm going to throw out some other questions just to mix things up a little bit. So let me start with you, Jeremy. So one of the major difficulties in doing haptics research in the wild could be getting reliable and controlled data. So what advice do you have on how to set up experiments to still get good results?
Oof. That's a doozy. You know, there are obviously so many confounds that come in when you're administering these kinds of experiments, from the environmental conditions that your participants are going to be exposed to the nature of their participants themselves, and to all the crazy things that they will do, you know, whether deliberately or not, to just mess up the experiment. And we've had many cases where we've had to throw out either entire participants or hours worth or days worth of collection of data, simply because of problems that the participants were not necessarily compliant with the instructions to the detail, or were equipment failures, right? So you deal with all of these sources of noise and sources that pollute your data. And I think there's probably a combination of strategic advice that I would give, which is, first, make sure you've got enough participants to cover for the shortfall you're no doubt going to experience, because you'll have to throw away a fair bit of data. Make sure that you're checking in repeatedly and frequently with your data collection. If you're gathering data in the wild by giving equipment to your participants and letting them run with it for a week, don't wait until the end of the week to verify that the data you've grabbed is valid and has been gathered correctly. There's nothing worse than coming back with all zeros, you know. And certainly, you know, make sure that the participants understand clearly what they have to do. If you can give them lab equipment rather than letting them rely on their own, that's been a big factor as well, especially given all the smartphone usage that we make in our experiments. Different devices, different battery life, different confounds of interaction with their own applications, those all create headaches. So just be prepared for all of those unexpected factors, and plan to deal with all the adverse effects that you'll encounter.
Sounds like it's spoken from a true experience there.
I had a full head of hair before we started these experiments.
All right, I'm going to turn to Evan next with a question. So what do you see as the next step for your syntax platform?
Yeah, so I think the first and foremost, what we want to see is feedback from the community. So we'd really like for people to start using this, letting us know like what they think of it and helping us find bugs, which I'm sure there are bugs in the software. But I guess there are a couple things that I personally would like to see added into syntax software. And the first is, you know, because of the way like we started from the audio world here, there's sort of this audio-centric like language to the programming APIs. So like we use words like volume and pitch, but really we might want to think more about how we can integrate like haptic terminology and even like haptic perceptual experiments into the API. So we're not like thinking in terms of volume, but maybe like haptic intensity or perceptual level that we're delivering. And then the other thing that I think is important, and it's just not something that we've gotten to yet, because we, you know, at this phase of the project, we really just want to get something that's working. But what we want to start thinking about is more in line with, you know, what Oliver talked about earlier today, and that's making like the process of designing haptic cues easier. And so, you know, like in the video, I designed a heartbeat. I didn't just like come up with that on the fly. Like it took me several attempts to get that just right. I even went as far as like looking at like an actual heartbeat waveform to get it right. And so to that end, I think what we could start doing is incorporating some of the work that I've seen recently in the literature, especially from Ali lately, which is sort of creating like these pre-designed effects that are like defined by parameters. So for instance, like rain or, you know, a heartbeat could even be one of them, where we change like the parameters associated with that effect, as opposed to like the actual parameters associated with the waveform. And so that would be probably the next step into like making this more usable by everyone.
So definitely a trend to sort of abstract the details of the signal design so that you can make it more accessible for a broader audience.
Yeah.
So I'll go next to, let me go to Sheila with a question. So you sort of, in some ways we're an outlier in discussing these tactile displays because most of the focus was on wearables, although others, your tactile displays are on the tabletop. But I wonder, what do you think are the applications for which these tactile displays are best suited? And what applications in augmented and virtual reality do you see as potential crossovers for tactile displays?
So it depends whether you're talking about tactile displays in general or microfluidics in particular. So tactile displays in general, I think, many of us in research, as well as, people who are visually impaired, would love a programmable tactile surface. And the finer the feature distribution we can get, the better. And if it has height variability, that's even better. So we can start to look at, surfaces that can be programmed in the same way as we can program sounds for speakers. We should be able to program textures for these kind of surfaces. So that's one area, and that's been sort of a holy grail, I think, for a long time. But also, I think the interesting thing about microfluidics, and there are, in fact, companies that are thinking about this, is that you can wrap it around a body part. You can turn it into a glove. You can do sort of wearable things with it when you can make features that are programmable within a texture that is malleable like that. You have a lot of possibilities available. So I think it will find its own in VR, probably most likely initially in gloves, but then who knows from there on.
Great, thank you for that. So I'll do one more of our sort of home designed questions, and I'll go back to the Q&A. So if any of our attendees have questions, please put them into the Q&A with the target of your question. Let me pick, well, let's go with Lynette next. What do you think are some of the challenges that need to be overcome to develop multisensory thermal and tactile displays and devices?
Well, one of the big challenges is obviously if you're using Peltier devices, what do you do with all that heat? So everyone who develops these really nice sort of wearable Peltier devices, like some I showed here, with little tubes going off into a sink of water, or I mean, a small element of water, but obviously people aren't going to be carrying around reservoirs of water for cooling. And one thing that I think is interesting outcome of our work is that warming seems to be a very interesting modality to use, and certainly in social affective touch that looks quite feasible too. And then you don't need to use Peltiers. You can use polyamide, you can use all sorts of deformable surfaces that you can put on the skin and heat it. There's also devices, I don't know whether anyone can see very well on my camera. This is, I'm not plugging this, I'm nothing to do with this company, but this is a device developed by Ember Labs. Their target audience is menopausal women, and it cools. And it's again one of those, and it's a form factor of a wristwatch, and it cools by about 1 degree, but it's interesting that you can develop things that are wearable. It doesn't have an active cooling system, but it has the potential again to explore that space of what you need in your display and can you get by with less rather than more.
Thank you. So let's take a question from let's see, I'll take Mark's question to Sheila. So you sort of dangled out this challenge that that we should tap into the non-sighted designers. And so the question is specifically, well, maybe we don't want to help industry anymore if they're already stealing, but the question is, how do we in industry tap into the non-sighted and non-hearing designers to get that perspective? Is there a way to reach this community?
Well, a lot of this community is fairly dispersed. I'm trying to think, I mean, looking at who's coming through PhD programs is probably one quick way to do it, but a lot of the innovation isn't happening at that level. I'm just thinking of somebody who won something called the Holman Prize, that is a prize given out by the Lighthouse for the Blind in San Francisco, and he won he won the prize for a program that he, as a blind person, was developing for, I think it was an iPhone, that basically is a bit like, you know, one of these planet watching things that you can do where you can point your camera or your phone at the sky and it'll tell you things. So it was an accessible version of an app, a bit like that, to allow blind people to engage in citizen science and to look for exoplanets, basically. And of course, as soon as he won the prize, Apple immediately snapped him up, and now he's working for them. So I think just embedding in the community is the best way to know, because the community knows who's out there. Also, there are things like the National Federation for the Blind that has a computer programming special interest group that keeps track. And then it also has a fairly active scholarship program for students coming through. And it's possible to find out from there who's going where to do what. So there are all sorts of channels, but, just kind of asking people who know these things is probably the quickest way to get there.
Thank you. So let me go to Ali with the next question. What technology development are you most excited about using in future haptic device development for XR applications?
That's an interesting one. I think it's difficult to say which one, because you cannot pick one. Already out there. I think a couple of technologies that we recently worked on, like both the TASB device and the Chasm device, they were like, I never thought that the haptic would be so convincing once I tried it. I remember working with you, and we had this device for speech communication, and then there was some form of a squeeze, and it just opened opportunities to see how well the squeeze could work. And then it kind of opened up opportunities to see how we could further solve some of these challenging questions. But quite frankly, it's all depends on the use case, the applications. If you are looking into surface displays, I think the Tesla Touch or electrovibration devices or friction displays, I see a lot of value. Current market is mostly the vibro tactile actuators are available. So I really want to see how even where we are currently incorporating a single actuator or maybe two actuators in a form factor, how could we actually progress from using multiple actuator and justify the value against the cost it adds into it. But yeah, these new skin devices which triggers the shear and the pressure, those are really, really fun haptic devices, and I really want to see how they progress and evolve in not only the consumer market, but also in the research domain.
Yeah, I'll add to that on my end. I think it's not so much a question of what I'm most excited about, it's what I'm most anticipating seeing down the horizon from further research efforts. And that's getting these kinds of miniaturization, densely packed units capable of providing that skin stretch type of effect, and possibly combined with kinesthetic feedback that can cover wide areas of our body with reasonable power demand, so as to elicit the rich kinds of interactions that haptics has the potential to deliver at scale, rather than dealing with these very small, we'll get a nice sensation on our fingertip or we'll have something on our wrist, but that's it. And you've got this big bulky apparatus around to support it. And then on the other side, I think it's embedding the intelligence in the controllers, so that we're not talking about haptics in isolation, but really haptics acting in concert with other modalities. So being aware of what visual and auditory stimulus we're delivering to the users, participants, whatever, and blending that in a seamless, engaging, augmenting manner that really deals with haptics as one element in a multimodal experience.
Also, I think your comment about multimodal, we touched on in the panel this morning, the richness that the combination of visual and haptic cues can give to an experience or an interaction with the environment, but also the dangers if there is mismatch there. So to your first wish list though, Jeremy, in these miniature devices, I think that's a great segue to the question I have for Heather. And that is, given your experience with fabricating devices and trying to minimize hardware, what would you say is the most critical item for haptic designers or hapticians to consider when minimizing their haptic hardware?
I think the most critical thing to consider is the perception, the human's perceptual limits, because you want to make sure not to over design the hardware. You want to make sure to actually understand what are the perceptual limits of the human in terms of what actual mode of touch you are displaying, whether it's thermal or skin stretch or slip or vibration or normal indentation. And once you understand then what are the perceptual limits, then you can decide what's the density of the array you need to build, if you have certain size actuators, how far apart can you put them? Because you really want to, in order to minimize the haptic hardware, we want to minimize the number of actuators on the body. So if we are trying to create like an array or a large scale wearable system, we have to know, where we're putting it on the body, what are the perceptual limits, and then we can decide what's like the best configuration of those actuators that we want, because there's no point in putting hundreds of actuators on the body if people aren't going to be able to tell the difference between two vibration actuators that are super, super close together. There's no point in adding all of these actuators. So we have to understand what's the perceptual limit? How close can you put two actuators, or how far can you put two actuators apart and people still distinguish them as a single actuator?
Right. Thanks for sharing your perspective, Heather. I really appreciate it. So Evan, there's a quick question to you in the Q&A on syntax. Do you have design models or parameters for virtual surfaces? And I don't know if maybe we want to transition to a little bit of discussion of the haptic textures libraries that was mentioned this morning as well. So I'll start with Evan on that.
Yeah, so syntax gives you the primitives to design feedback for surfaces. It does not give you pre-designed effects for rendering surfaces, which is sort of goes back to what I was saying earlier. That would be the next step here, is giving you like parametric effects that you can use to create surfaces or different types of things that you experience in typical haptic environments. That said, syntax will import haptic effects that you can find in other haptic libraries, such as WAV files. So you can still use those with the programming API.
Thanks. And there was a mention earlier, there is a textures library. I don't know the official name of it. Does Heather, is that something you're familiar with from out of Catherine's group, where she was using a different technique to render textures through a voice coil actuator on a stylus?
I don't know this one. Sorry.
Okay. It was there this morning in my head, but a long day of Zoom has taken it away. But I would, if you're interested in texture libraries, I would check out the resources from Catherine Kuchenbecker's group. So there's a question to, oh yes, the Pen Haptic Texture Toolkit. Thank you.
Okay, that's the one I created. I wasn't sure if you were talking about a new. I wasn't sure if you were talking about a new one. Sorry, Marcy. I thought you were talking about a new one that she had created. No, okay.
No, it's your seminal work.
Okay. There. Yeah, I know this one quite well.
Do you want to give us the 30-second sales pitch for it?
Sure. Okay. Yeah. So this is work I created in my PhD, and it includes 100 textures. We deal with textures as felt through a tool. So we it's data-driven textures that we have recorded and modeled. There's texture models as well as friction models, and there's it includes all of the data, 2 data sets, 2 data recordings for each texture, as well as all of the rendering code used to actually render and create these synthetic textures using an Omni.
Awesome, thank you, Heather. So I think the remaining question in the Q&A is being addressed with a typed response. So I just want to open up to our panel for some closing thoughts. We've had a whole day of discussion about design of haptic interactions, devices, evaluation, some of the challenges of combining different kinds of haptic experiences simultaneously. So I don't know if you want to just share a closing thought or challenge for our attendees going forward to see how we can move the field in exciting new directions.
So perhaps if I can sort of cheat and use the opportunity just to challenge Heather on the point that she brought up about dealing with the actual perceptual density of our mechanoreceptors in terms of designing systems that deal with that. I'm just wondering whether as a field or as a body of professionals in the area, we're dangerously kind of following blindly the naive, simplistic tests like the 2-point discrimination to determine what the actual density of perceptual discrimination is. And that if we had an apparatus that could render 1,000 points per square centimeter, even though our TPA says, oh no, those are going to be perceived as identical, whether we would have a better characteristic of understanding the texture or understanding different properties. And it sort of reminds me of all the work in human vision, where we said, oh yeah, 30 frames a second is all you need for fluid perception of motion. But there's no question that as you bring it up into the hundreds, we get more out of the signal, even though we can't sort of break apart the frames more effectively. And I think haptics may well turn out to be very much the same in that regard. So I just caution against sort of taking the simple measurements we've been capturing and using those to guide us in terms of the necessary limits of the apparatuses we end up building.
Right, Jeremy, I completely agree, because the measurements we get are very, very simplistic, and they don't take into account a lot of things such as the material of the contact or the size of the contact or temperature, ambient conditions, or age of the skin. And so taking those at, you should just take those, is as a to help you inform your design, but not necessarily say for certainty that this should be the size of or the spacing of your array, but maybe set a certain limitations or certain guidelines of what would be an appropriate array. Also, in terms of rendering, it depends on what you're trying to render. For example, if I'm trying to render social touch and I know people are going to only touch with an open hand, then I can probably deal with actuators that are much more spaced apart than if I'm trying to deal something, for example, with contacts that are going to be more point contacts on the arm. So not only does it have to deal with, your perceptual capabilities, but also what are the limitations that you're trying to render. So if you're trying to render something super fine texture, then yes, you would want actuators very, very close together.
So I'd like to add my comments to that. I think one needs to realize that all those benchmarks are absolute thresholds, and nothing we do in haptics should be an absolute threshold level. It makes absolutely no sense to be working at the noise plus signal detection point. So, and the other thing is that when people talk about the best areas in terms of frequencies or amplitudes, that's often related to single types of mechanoreceptor, which again is meaningless in the context of all the phenomena that we're interested in presenting, where obviously most sensors in the skin are active. And so I think for a long time, a lot of people have got very bound up in the idea that we need to go in this 200 to 300 hertz range because that's where optimal sensitivity is. But that's only an absolute threshold. It's nothing in the sphere of how we interact with everything in the real world. So I think we should abandon tying things to mechanoreceptors at all and use the absolute threshold only as sort of something that you have to get out of your system at least as minimum performance. And if you're under that, you're having real problems with perceptibility. And the other thing is that often even historical studies on perception and neurophysiology, when you pose the question differently, you get different results. So just to use thermal sensing as a good example of that, that everyone has always said that thermal sensing is very poor at localization, that you can't tell very accurately where things occur on the body, and that people can mistake the front of the torso to the back. But then when we did these studies on these sort of space-time illusion, people reliably perceive things in exactly the same way that you do in vision and hearing. So again, the spatial information was there, you just sort of had to extract it in a way that made some sense to the central nervous system. I don't know how or why it does that, but some areas of the brain that are multisensory and can process those signals. So I think we always need to think of the bigger picture of how the brain responds to these inputs rather than being focused on these sort of particular pathways from the periphery to the brain.
Can I follow up on Lynette's answer?
Please do, Sheila.
So recently I've been looking back again at some of the work that Vincent Hayward did on perceptual invariance for touch, and this is following on Gibson's work on things like perceptual invariance for cues for vision, where you might track the angle of expansion of the retinal image in order to figure out whether a ball is going to hit you or not. And I think we're probably getting to the point where in haptics where we're going to start moving away from these basic individual percepts, as Lynette was saying, the response of individual receptors, to looking at these more sort of large-scale invariant qualities that we perceive. Because certainly for 3D vision in VR, it was moving towards perceptual invariance in vision that allowed the fields to move forward when cameras weren't great, when you had to look at how movement was integrated into seeking image properties. And I think in haptics we get that for free because we're always moving to acquire stimulation. But I think maybe that's where we're going to move towards now in looking at these higher level contextually framed percepts.
I think these are really important points, and really maybe the next frontiers for us to explore perception of multisensory cues and distributed cues across the body, and how we integrate that information to really maximize information transfer and just the user experience in these environments. So, yeah, go for it, Ali.
Closing remark. So one of the things is that we are actually living in a very challenging time, and at the beginning of this year, when this whole thing started, the one thing that we actually missed or lost is the touch. So perhaps this is an opportunity for us to see where new opportunities may come or currently available. So thinking broadly about how what we have missed during this last year, how we could actually connect this by using digital mediums. So this is I think we have an opportunity. I think we also have a responsibility as well to see how we could leverage this challenging time to something that will be useful for future generations.
That certainly has been something we're all missing out on, unless we've, except in our tiny little pods of safe groups.
And Marcia, I'm pretty sure every haptician or haptic researcher has been thinking about it since it started.
Absolutely, absolutely. So any other final thoughts from our panel?
How about a big round of applause to Marcia for organizing this, and Zane and putting it together. You guys did a fantastic job, and especially having to deal with me in my late submission of the video and so on. So kudos to the two of you. You really did a great job.
Thank you, Jeremy. Evan, you were going to say something?
Yeah, I was just going to say, you know, we have 40 of the syntax kits floating around out there now. So we'd be really happy to get some feedback and hear what you guys make with them and share it with us. And we'll consider putting it on our website even. So we're looking for people to contribute to this project, whether that's through, you know, the code, tutorial content, or original haptic displays that we could potentially share with other people.
Great.